Thank you for the introduction. So electric-based peripheral nerve stimulation is commonly used to treat chronic pain and inhibit hyperactive motor reflexes in several diseases. Implanted electrodes deliver fast repeated electric pulses causing paresthesia, felt as mild tingles. And the drawbacks of the technique are invasiveness when using implanted electrodes, or the poor penetration and spatial control when using surface electrodes. Focused ultrasound has the potential to non-invasively and very targeted excite the nerve deep in the tissue. Based on our previous study in mice, we have strong evidences that acoustic radiation force is the primary mechanism. However, when you increase the pressure, you can introduce cavitation. And when you increase the pulse duration and pulse repetition frequency, you can also introduce thermal effects, and both can contribute to the neuromodulation effect. So our goal in this study is to develop a clinical system that allows the investigation of the acoustic radiation force as the primary mechanism. And for that purpose, we control and monitor the cavitation, avoid cavitation, and temperature effects. So we have two image-guided experimental setups to evaluate cavitation, temperature, tissue damage, and to perform our preliminary tests in human. The choice of the frequency is based on the size of the target. So in mice, we use 3.1 megahertz to target the sciatic nerve, and this frequency provides a focus of 0.4 millimeters. In human, we use 1.1 megahertz transducer to target the median nerve, and we have a focal size of 1.7 millimeter. And to compare across experiments with different frequencies, we use the mechanical index that is defined by the pressure divided by square root of frequency. So here you can see an example of excitation, pulse twitch, from the excitation of the sciatic nerve in mice using single pulses. When we used wire and needle thermocouples, we did not see any temperature increase even for the highest MI12 for a very short pulse of 1 millisecond. In our positive control, we sonicated at 1 hertz PRF, and during 5 minutes, we observed a mild temperature increase of 1.7 degrees Celsius. So in conclusion, we can control the temperature by keeping the pulse short and reducing the PRF. And as I said before, if we increase the pressure, we can introduce cavitation. And we demonstrate in this validation in mice that we can track spatially the cavitation. And this is done by tracking ultraharmonics and broadband emissions as indicative of cavitation. So when we sonicated also in mice using 12 high MI for a short period, 1 minute, we did not see tissue damage. However, when we sonicated the surface of chicken breast samples, we did observe tissue fragmentation for MI level of 7.4. So we are operating at MI levels lower than that in humans. So based on these validations, we developed our clinical setup. We use a robotic arm to place the transducer on the arm of the volunteer. And we use image guided, as was asked before how we guide. We can see the median nerve very well, and we target the median nerve using B-mode. And the volunteer was given a button to report sensation during blind sonication. You can see in this example in gray when sonication happened, and when the volunteer reported sensation in red. The sensations were divided into groups. Skin sensation, this was considered a non-modulatory effect. As Mike just said, if we don't hit the nerve, we don't have. And also nerve activation, described as light cramp, thumb or hand spasm, tingling, twitch, pulse traveling through the arm, and so on. We were able to get nerve activation for a wide range of MI. However, when we increased the MI, we observed more of the skin sensation. So we are now evaluating MI levels mid to low from 2.5 and lower, so we can get more of a nerve activation. And the temperature measured at the skin was negligible, so we consider completely safe. In conclusion, we achieved safe sonication of the median nerve in humans indicated by variable sensations at MI levels where no cavitation is expected, and the temperature effects were negligible. Our future work include improving targeting using tissue displacement imaging. As you see, this is actually my arm on the top. You can see exactly where the focus of the ultrasound is. And also we want to include the passive cavitation imaging so we can maximize the acoustic radiation force while avoiding the cavitation. And also we want to monitor the sensations quantitatively using SEP, somatosensory evoked mutation. And finally, we expect to observe motor responses. Thank you for your attention.
The MIs you are using are above what the FDA would recommend, at least for diagnostic ultrasounds. I'm just curious how you managed to get that through your ethics panel.
Correct. So we tested up to 4.6 MI, but we did get nerve activation for lower MI, lower than 2, lower than 1.9.
Right, but your ethics panel were fine with going above what the FDA would normally approve for diagnostics?
We believe that as long as we don't observe cavitation and temperature effect, it should be fine.
Okay. Yeah.
Thank you.